Well, let's analyze an RL circuit under equilibrium conditions, steady state conditions, and then we'll close a switch and figure out the values immediately after closing and a long time after closing. So here's the circuit, and it's a pretty simple circuit. It's just not the most simple RL circuit because we have this switch that connects a wire across here then. But initially, the steady state conditions of this circuit with the switch open. Let's figure the voltage AC, the voltage CB, the currents through this resistor, the switch, and this resistor. All right. Well, I steady state. At t is equal to 0, this closes. But just before it closes, we have this current. And the current is simply going through those two resistors and the inductor. Steady state means there's no change in current. No di dt, therefore no LDI dt. No voltage across the inductor at that point. So very simple. Let's just go ahead and define the currents. And we have I big R, we have I switch, and we have I through this one. Just call it I through the inductor and through little r. So the steady state current is EMF over R total. Our total is just 50 and 150. It's a series circuit going around there. Switch is open. Gives us 36 over 200, 0.18 amps. Now, I through little r is, oh wait a minute, it is 0.18 amps because it's in series. This is the condition right after you close the switch at time t is equal to 0. So the current through R is that same value because the current can switch infinitely fast in the inductor. So the inductor forces that current to be the same as it just was, and then it immediately starts changing. It's kind of like there's an acceleration, but the velocity doesn't change instantaneously. All right, we're going to do a Kirchhoff loop around the outside of the circuit. So we have the battery 36 minus 50 IR plus LDIDT. Right, that's a drop. Right, and minus 150 I, and then that's all equal to 0. Okay, now this is a little bit tricky. We got to be careful about this. I said it's a drop, but depending when exactly you look at it. In any case, LDIDT, when you close the switch, then this voltage across here, it actually is going to be going, there's going to be a rise across here, isn't there? Because it's going to force the current to move around. And so it goes negative to positive, and this goes then positive back to negative. Drop across there. In any case, this is a loop here. There's a loop, and so whatever is across here has to be across here. These are across each other. So this LDIDT is 150 I, right? From negative to positive. So it's really a rise. Then we have those negating each other. 36 equals 50 IR. IR is 0.72 amps. So the current through this resistor went from 0.18 instantaneous, it's 0.18 because that's the steady state through all these components. And then this current jumped immediately to 0.72 amps. So closing that switch had a big effect. Well, it makes sense because it kind of basically shorts out all this stuff and provides a direct loop around here. So that's pretty easy to analyze. I through the switch is, well, it's this current coming in minus what's leaving. I big R minus I, 0.72 minus 0.18, 0.54 amps. Now, VAC, well, that's simple. 50 times IR, which is 36 volts. Now determine the values after a long time has passed. Well, that will be done considering after a long time has passed. Well, this resistor doesn't need any time at all to reach its equilibrium or quiescent steady state values. But this side does, and when it does, there's no more change in current, and the inductor is, well, if you look at this loop here, when this thing is done collapsing its magnetic field, current quits flowing. Whichever way it's flowing, it quits, and it was going clockwise here, so it just quits flowing. And so VAC is 36 volts. That side hasn't changed. It's just that single loop, 36 rise, 36 drop. VCB, well, there's no current at all in that loop at this point, so it's just 0. The current is 0 in that inductor and the little r equal to 150. Then I to the big R at this point is just simply the current going through the switch. They're both the same. It's what current flows in a single, 36 volts with 50 ohms. So that's 36 over 50, 0.72 amps. And that basically analyzes everything going on there at steady state, and then after you make the change of closing the switch, and then after a long time has passed again. Those are pretty easy. Now let's do the intermediate values from the point that you close the switch to when things reach steady state conditions again. Okay, so let's go ahead and do that. Here's the circuit, and the current through the inductor equals I steady state e to the minus r over LT. That's simple. That's 0.18. E to the minus r is the resistor in series with the inductor is 150. The inductor is 4. And we can say this because you see this loop here. Basically, by closing this switch, we've effectively eliminated all this from this over here because C and B are at the same potential. So it's the same thing as just erasing all this out of here. Okay, this loop doesn't have a potential difference from C to B. All right, so there's the answer. 0.18 e to the minus 37.5 t amps. Well, that was easy. Now let's get the current through the switch. Well, the current through the switch, Kirchhoff's point rule, IR minus I. And so we have 0.72, that was constant, minus the value we got for the current through the inductor. So there's the answer. 0.18, 4 minus e to the minus 150 over 4t. So let's graph the current through big R. Well, that's simple. Constant, 0.72 amps. Now, the current through the inductor looks like this. It starts at the max value, which was 0.18 amps, and then trails off to 0. Finally, the current through the switch, well, basically we're just graphing this. At t is equal to 0, we just got 0.18 times 4. I'm sorry, times 3. 4 minus 1 is 3. And then it goes to infinity, where this is 0. So it's just 0.18 times 4. So that starts at 0.54 and ends at 0.72 and rises like you would expect it to. So there's the analysis of that particular circuit problem with a resistor and an inductor. Okay, well, let's do this little problem where we're going to find the magnetic energy that's left in this LR circuit after 3 time constants. And here's the current. We know the current trails off. 3 time constants, we know it's almost all the current's gone. So what magnetic field energy is left? A couple basic concepts. First, the current. I0 e to the minus r over LT. And then the potential energy, 1/2 Li squared. So it's based on the current because it produces the magnetic field in which contains the energy, the magnetic field energy itself. So the time is 3 tau. Now tau is 1 over this, so it's L over R, so 3L over R. There it is. All right, well, this should be easy. The potential energy at 3 tau compared to the potential energy at the beginning is simply 1/2 Li, I0 e to the minus r over L times the time, 3L over R, all that squared over 1/2 L I0 squared. Well, this wonderfully cancels almost everything. So that's all gone. And then in that exponent, we have almost everything canceling there. This whole thing reduces to e to the minus 3 squared, which is e to the minus 6. And so we have that the remaining potential energy is just 25 10,000ths of the original. Almost all gone. Goodbye.